All right, let's talk about section 6.4, logarithms and logarithmic functions. So today we're going to learn a new type of function. We've been talking about exponentials and exponential functions and exponential behavior. All right, and so in this section, we're going to start talking about the inverses of exponentials. So before we talk about that, let's talk about what inverses even are. Okay, so we learned about this a couple of chapters ago, but inverses are, the inverse of a function is the reflection of that function over the line y equals x. Okay, so the inverse of this function that's graphed here would be something like this. Whoop, missed it a little bit. Now that should sort of curve over like that. So it's not, I'm not perfect at sketching this, but you get the idea. It's reflected over the line y equals x, okay? And we talked about some applications of inverses before. What we're talking about here, though, is, or a reasonable question might be, what is the inverse of an exponential? What would that look like? Well, here is just a random exponential function. It's probably like 2 to the x or something. Or maybe it's e to the x, it doesn't matter. But it's an exponential function. The question is, what's the inverse of this? Well, one way we can get an inverse is just change around all of the x and y points. So for instance, this is all the points. We can change around the x and y's in each of the points on the graph. So if this is at 0, 1, we could plot over here 1, 0, which would be here. Okay, and if this is at negative 1, barely anything, we can go down to barely anything, negative 1, which would be like right here. And so if we did this enough times, what we'd end up with is some graph that looks sort of like this. It's the inverse of an exponential. Okay, it's reflected over the line y equals x here. And so this graph here, this thing, the inverse of an exponential is called the logarithm. Why is it called a logarithm? That's just the name they came up with. All right, for inverse of an exponential. That's all it means. Okay, so don't get freaked out by this new word, logarithm. It just means inverse of an exponential. Okay, you might even write that down. Okay, so I'm going to show you how we can take any exponential and turn it into a logarithm. So if this is the format of my exponential equation, then I can change this to a logarithm in this way. I can take the log with the base b of y, and that will equal x. Okay. Sometimes it's easier to go from logarithm to exponential. So this base right here is the base of your exponential. Whatever it's equal to is the exponent, and then y is the number that is the result of the exponential. And so the way I like to remember this is the base raised to the power equals the number. So base raised to the power equals the number. Base raised to the power equals the number. So we're going to look at some examples of this in just a second. It's important to understand that this definition runs both ways. Okay, so you can get from logarithm to exponential in this way, or you can get from exponential to logarithm in this way using this definition. Okay, so this is really important. So if I have something like this, log base 2 of 8 equals 3, how do I turn that into an exponential? Well, I can do it in this way. I identify what the b is. It's 2. The y is 8. And the x is 3. Or as I like to think about it, the base raised to the power, so 2 raised to the 3, equals the number 8. Okay, and you can check in your calculator. 2 cubed is 8. Now, on these problems, you do not need to solve anything. You're just taking a number or an equation in one format and changing it to a different format. Okay, it's very similar to if you had something like 5x equals 7. 5x equals 7, and I said, okay, what's the inverse of multiplication? And you said, well, it's division. So you divide both sides by 5, and what you end up with is x equals 7 divided by 5. Over here, it was 5 times the number, and over here, it's when you do the inverse, you get 7 divided by that number. Okay, so it's a very similar thing. We're not simplifying or solving anything here. We're just moving things around. This is one perfectly fine way to write this equation. This is another one. Okay, let's go over here. Do the same kind of thing. So here I'm going to take the base, which is 4, raised to the power, which is to the right of the equal sign, so negative 4, equals the number, which is 1 over 256. Okay, again, you can label all the numbers if you want, but I'm just following the definition here. All right. If we can write a logarithm as an exponential, as I said, we can write an exponential as a logarithm. So here I have 15 cubed equals 3375. Now, again, there's nothing to solve here. We're changing the format of the number. So you can see that this is our base is 15, x is 3, and y is 3375. So when we convert this to a logarithm, it's going to become log of the base, which is 15, log base, and then 3375 is the y, and that equals 15. Okay. Another way that you can think about this. Now, if you're okay with thinking about it like this, that's fine. But I want to give you one more way to think about this. And put it on the back. So we had 15 to the third power is equal to 3375. You can think about it slightly more algebraically. So if you take the log base 15 of the left and the log base 15 of the right, and that's how that's read, by the way, log base 15 of whatever is there. Log base 15 of 15 to the anything, these are inverses of each other. So I get 3 is equal to the log base 15 of 3375 on the right. Okay, so this must equal 3. This is what we got over here, following the definition. So you can think about it however you want, right? So I've given you a couple of ways there. Okay, let's actually apply this. Oh, and by the way, this is going to seem like a useless operation. Like, why are we just moving these equations around? Okay, well, this is a setup for applications later on. If you don't understand how to go from logarithm to exponential and vice versa, then the problems that we're going to deal with later on are going to be very difficult. So you've got to understand the mechanics of them first before you go on to new stuff. Okay, so evaluate the logarithm. So up here we had log base 2 of 8 equals 3, and we were just moving things around. But what if I didn't give you the 3? How would you figure out what the log base 2 of 8 was? Because that's a number, right? Well, here's how we're going to do it. We're going to say log base 16 of 4, that equals some number. I'm going to call that number y. Okay? What is that number? I don't know. But if I set it up as an equation, I can rearrange it as an exponential, and then maybe I can figure it out. So I can rewrite this as as 16, that's our base, raised to the number, so that's y, is equal to 4. Okay, and so you ask yourself then, what raised to the fourth power, what do I raise 16 to get 4? Or another way that you can solve this, or think about this, is can I make the bases match? So here I can, 4 squared is equal to 16, and that's equal to 4 to the 1. So I can write this, that 2y is equal to 1, and solve for y. And so I get y equals 1/2. Okay, in other words, to sum up, I can write this in a different color for your learning convenience. Log base 16 of 4 is equal to 1/2. Okay. All right. So that's all we're going to do with logarithms in terms of evaluating them and moving them into exponentials and back. All right. The last thing we're going to talk about in this lesson is graphing. Okay. So if we want to graph something like log base 5 of x, we can expect it to look something like this because logarithms sort of look like this. All right. But what exactly is it going to look like? Well, here's what we're going to do. We're going to use Desmos to our advantage here. We are going to go pull up the functions here. And we will go to miscellaneous, and we've got this log base a command here. So we'll go log base 5 of, and then we'll put x in, and there's our graph. Okay, and we can go straight to turning that into a table. You notice that it's not defined to the left of 0. So the domain of this function, which we'll write down, I didn't ask for it, but we'll write it down here, is going to be just when x is greater than 0. All right, and the range is going to be all real numbers. But let's get this graphed first. So, whoops. Okay, so we've got the point 1, 0 there, and then we've got 5, 1, and then this is a vertical, whoops, you can't see that. This is a vertical asymptote right here. So really you only usually need 2 points and to know where the asymptote is. There. The domain of this is x greater than or equal to 0. Sorry, greater than 0. Greater than 0. And the range is all real numbers because it goes forever up and down, right? This is the general form of a logarithmic function, very similar to the general form of any other function, any other type of function. So h is your horizontal shift, k is your vertical shift, a adjusts the stretch of the function, and b, we're not going to really worry about how b changes the graph. We won't ask you to analyze that. Okay, so general form right there. So you could take, you know, the functions will get more complicated than this, than just log base 5. Maybe you've got x minus 3 in there and plus 2. And maybe your base is something like, instead of 5, maybe it's 1/3 or something like that. Well, you have to use parentheses, I guess. Maybe I can't put in a fractional base. I guess you can't put in a fractional base. But anyway, you get the idea. So you can go in and adjust those functions as needed, right? Last thing I want to talk about is on the back. So if you flip to the back page, you will see something like this. Now, it didn't copy fantastically well, but I want to talk about applications of logarithms because they show up all over the place, especially in the sciences. Anytime we're dealing with very, very, very large numbers, huge scales, or very, very small numbers, like extremely small values, like in chemistry when we talk about pH, for example, log scales or logarithms are very useful. Let me show you why. So over here in this chart, we have the energy release of earthquakes at different magnitudes. So you might have heard things like a magnitude 7.0 earthquake, right? Well, those magnitudes are over here on the left. And what I want you to notice is if we look at 56 million here, right? 56 million kilograms of explosive equivalent. Over here, that is a magnitude of 6. If we go up and we multiply that by 1,000, we get this number here. And that magnitude is 56 billion. And that is only 2 higher on the magnitude scale. And the reason for that is because this is a log scale. All right, so a question that we might ask, like if we're over here in the energy release column, right? And we say, okay, well, I've got 56 million tons of or kilograms of explosive equivalent, right? And I want to know, well, okay, what if we just said 10 to what power gives me 56 million, right? So like 10 to what power gives me 56 million? Because that number right there is going to be a lot easier to manage than 56 million, or as it goes up, 56 billion, or even higher and higher and higher, right? So you go, okay, well, this would be the log base 10 of 56 million is going to be equal to y. So that number is going to be, whatever this number is, and we can figure it out with the calculator, is going to be the magnitude of the earthquake. Okay, so the big takeaway is just that these show up all the time. pH scale, earthquakes, magnitude scale, they show up in a lot of places when we're dealing with very large numbers or very small numbers. And so I just wanted to throw that out there as this is just not math for math's sake. It's actually one of the more applicable areas of mathematics. And I think that wraps up section 4.